Dear students, I am Kavita BS, Assistant Professor, Department of Physics of Government First Grade College, Tiptur. In this class, I will explain the derivation of equation for coefficient of viscosity. And this topic is in BSc course, Physics subject, paper 3rd, Thermal Physics, Radiation and Optics 1. And this topic is in the lesson Thermal Physics of Unit 1. Let us start the class. First, let us discuss transport phenomena and then I will explain the derivation of equation for coefficient of viscosity. In fluid mechanics, certain phenomena such as viscosity, thermal conductivity and diffusion can be referred as transport phenomena. Here, the transfer of momentum, heat and mass of gas will take place in order to attain equilibrium condition. That is, in viscosity can be defined as due to the variation in velocity in different part of a gas will leads to transfer of momentum among the gas layers will take place, and this phenomenon is known as viscosity. In viscosity, there will be a transfer of momentum will takes place among the gas molecules due to the variation in velocity. And in case of thermal conductivity, due to variation in temperature in different part of the gas will leads to transfer of heat energy from the region of higher temperature to the region of lower temperature, and this phenomenon is known as thermal conductivity. In thermal conductivity, heat energy will flows from higher temperature to the region of lower temperature, so that the temperature will remain same in all the part of the gas. And the diffusion, this phenomenon can also define in similar way. That is, due to the variation in molecular density in different part of the gas will leads to movement of gas molecules from the region of higher concentration to the region of lower concentration. Here, the gas molecules will move from the region of higher concentration to the region of lower concentration, so that the gas molecules will equally distributed. Hence, and this phenomenon is known as diffusion. So, viscosity, thermal conductivity and diffusion are referred as transport phenomena due to the transfer of momentum, heat and gas molecules. This is about transport phenomena. Now, we will discuss the derivation of equation for coefficient of viscosity. For that, let us consider a gas which is flowing over a solid horizontal surface. This is OX represents solid surface and the gas which flows over this solid surface. And let us also assume that the gas is made up of large number of closely spaced layers, and the velocity of the gas molecules which are in contact with this solid surface be 0 or 0. The velocity of the gas molecules which are in contact with the solid surface, or the molecules in the layer which is in contact with the solid surface will have 0 velocity. Then the term dV by dy, here the term dV by dy represents velocity gradient, that is nothing but the difference in velocity between the two consecutive gas layers. Here dV by dy is the velocity gradient, that is difference in velocity between the gas layers, between two consecutive layers, and it is increases with as we move from solid surface to in vertical direction. That is, as we move in vertical direction, that is in along y axis, it is increasing. Then let us consider a layer B which is at a certain distance from the solid surface. V is represents one of the layer of the gas and it is at a certain distance from the solid surface. Then let us assume that the velocity of the gas molecules in this layer will have V, that is V is the velocity of the gas molecules of this layer, and all the gas molecules will have the same velocity, and that is equal to V. And let us consider two more layers, that is P and Q are the layers which are on either side of the layer B. P and Q are the two layers which are on either side of the layer B, and these two layers are at equidistance from the layer B. P is at distance lambda and Q is also at a distance lambda from the layer B. Here the lambda represents mean free path of the gas molecules. Here we are considering the two layers P and Q on either side of the layer B, which are at equidistance from the layer B, and that equidistance is equal to mean free path. That is, in order to avoid the collision of gas molecules while moving between the two layers. In order to avoid the collision, we are considering the two layers which are at a distance equal to mean free path on either side of the layer B. Then first let us know the velocity of the gas molecules of the layer P and then in the layer Q. First, since the velocity of the gas molecules of the layer is V, then the velocity of the gas molecules in the layer P is equal to V plus lambda dV by dy. The velocity of the gas molecules in the layer P must be equal to V plus lambda dV by dy. Similarly, the velocity of the gas molecules in the layer Q is equal to V minus lambda dV by dy. This term represents velocity of the gas molecules in particular layers. And then let us calculate by the mathematical calculations, that is the number of molecules crossing the unit area of B. Here we are calculating the number of molecules crossing unit area of B in unit time, that is this layer along this layer, and that is equal to 1 by 6 of Nc. Here N represents number of molecules per unit volume and C represents average velocity. 1 by 6 term represents the average distance, the average molecules which are moving in any one particular direction, either upward or downward. If we consider a cube, in cube has 6 faces, then the 1 by 6 of total number in an average 1 by 6 of molecules will move either any one direction, that is up or down, left or right, or front or back. Hence, in an average, the number of molecules crossing unit area of B in unit time is equal to 1 by 6 of Nc. And mass of the molecules crossing unit area of B, that is given by, if we multiplied this term by m, we get the mass of the molecules crossing unit area of B, that is 1 by 6 mNc. This amount of mass will crossing unit area of layer B. Then next we will calculate the momentum, that is the momentum carried by the molecules from the layer P. The momentum carried by the molecules from the layer P crossing unit area of B in downward direction, that is equal to mass times velocity, that is 1 by 6 mNc into V plus lambda dV by dy. This term represents momentum carried by the molecules from P crossing unit area of B in downward direction. Similarly, the momentum carried by the molecules from the Q, the momentum carried by the molecules from the layer Q crossing unit area of layer B in upward direction, that is equal to mass times velocity. The velocity of the molecules of this layer is V minus lambda dV by dy. Then mass is 1 by 6 mnc. Then mass into velocity gives the momentum carried by the molecules from the layer Q crossing unit area of layer B in upward direction. Then the net transfer of momentum is given by the mathematical calculation, that is equal to the difference of those two. That is, if you calculate the difference, that is the net momentum lost by the molecules of the layer P or the net momentum gained by the molecules of the layer Q is equal to 1 by 6 mnc into V plus lambda dV by dy minus of 1 by 6 mnc into V minus lambda dV by dy. Again, on simplifying this term, we get, that is 1 by 6 mnc into lambda dV by dy plus lambda into dV by dy. Here V term, that is plus V, is cancelled with minus V. Then on further simplification, we get 1 by 6 mnc 2 lambda dV by dy. Finally, we get the net momentum lost by the molecules of the layer P or net momentum gained by the molecules of the layer Q is equal to 1 by 3 rho C lambda dV by dy. Here the term in the place of m1 m into n, we can write rho, that represents density of the gas. Then that is equal to 1 by 3 rho C lambda dV by dy. This is nothing but the net momentum lost by the molecules of the layer P or gained by the molecules of the Q must be equal to backward dragging force acting per unit area on B. So, the layer P above the layer B tends to accelerate the motion of the molecules of the layer B. At the same time, the molecules of the layer Q, that is below the layer B, will tends to reduce the velocity of the molecules of the layer B. Here, the molecules of the layer P will tends to accelerate the motion. At the same time, the molecules of the layer Q below the B will tends to decrease the motion or velocity. Hence, there will be a backward dragging force will acting per unit area on B, and this backward dragging force is equal to gain or loss of momentum, that is the net momentum gained by the molecules or lost by the molecules of the layer Q. Hence, that force is equal to 1 by 3 rho C lambda dV by dy. The net momentum lost or gained by the molecules is equal to 1 by 3 rho C lambda dV by dy. This is nothing but backward dragging force, that is nothing but viscous force or tangential force. And by the definition of tangential force, we have N dV by dy. This is nothing but force, tangential or viscous force. This force must be equal to this force. This is nothing but transfer of momentum, and this is dragging force. These are one and the same. Then on equating these two, we get N dV by dy is equal to 1 by 3 rho C lambda dV by dy. The tangential force is directly proportional to velocity gradient. This is proportionality constant, that is nothing but coefficient of viscosity. Then viscous force is proportional to velocity gradient. and this is constant of proportionality. Then on equating these two, we get eta is equal to, by cancelling this term, that is dv by dy on either side, we get eta is equal to 1 by 3 rho c lambda, or eta is equal to 1 by 3 mn c lambda. On substituting the value of lambda in this equation, we get, that is eta is equal to 1 by 3 mn c into 1 divided by square root of 2 into pi sigma square n. Then finally we get eta is equal to m into c 3 root 2 pi sigma square. This is the expression for coefficient of viscosity. From this equation, it is observed that coefficient of viscosity is directly proportional to mass of the gas molecule, and it is directly proportional to square root of the absolute temperature, since c is the average velocity, and this average velocity is directly proportional to square root of the absolute temperature. Hence eta, that is coefficient of viscosity, is also directly proportional to mass and square root of absolute temperature, and it is inversely proportional to square of the diameter of the gas molecules. And this is about equation for coefficient of viscosity, and these are the textbooks for your reference. College Physics, that is volume 1, refresher course in physics volume 2, heat and thermodynamics and statistical physics, and understanding physics second semester, concepts of physics and fundamentals of physics. These are the some of the textbooks for your reference. Thank you.